In continuation of previous lecture based on gamma function, we take another theorems related to that. So here we will prove to prove the values for gamma 2 is equal to 1, gamma 3 is equal to 2. That is also we can write a factorial 2. Gamma 4 is equal to factorial 3, and similarly gamma n plus 1 is equal to factorial n. So we shall prove these all the formulas. We can say that by using the definition, that means the definition of this. We have already proved this gamma n plus 1 is equal to n gamma n. So we write down as we know that gamma n plus 1 is equal to n gamma n. So we want to prove the first part. So by putting n is equal to 1 in, we give the equation 1. In 1, we get gamma 1 plus 1 is equal to 1 gamma 1. So this is LHS gives us gamma 2 is equal to 1 gamma 1. Gamma 1 we have already proved the value of gamma 1 is equal to 1. So we can see that gamma 1 equal to 1 we have already proved. So now we put the value of gamma 1 equal to 1. So we see that gamma 2 is equal to 1. Gamma 2 equal to 1. So this we can say that this 1 is equal to the factorial 1. So you can write down in another terms that this equal to factorial 1. So this is another way 1 can be written as the factorial 1. Now we shall prove gamma 3 equal to factorial 2. So put n is equal to 2 in equation 1. So we get gamma 2 plus 1 is equal to 2 gamma 2. So when we put n equal to 2, so LHS gives us gamma 3 is equal to 2 gamma 2. So what is the value of gamma 2? Gamma 2 value is 1. So 1 into 2, this can be written as 1 into 2. So basically we can write down this is equal to 2, or also we can write down this as factorial 2. So 1 into 2 gives us factorial 2. So you can see that gamma 3 is equal to factorial 2. So the value of gamma 3 is equal to 2, or we can say that factorial 2. So we remember these. Now we move further. So we can solve for gamma n equal to 3. So put n is equal to 3. So we get gamma 3 plus 1 is equal to 3 gamma 3. So this equal to gamma 4. Gamma 4 equal to 3 into gamma 3. Gamma 3 value is 2 into 1 is factorial 2. So this gives us 1, 2 into 3 gives us factorial 3. So gamma 4 is equal to factorial 3. So gamma 4 is equal to factorial 3. So in general, we talk about the general terms. General term is n. When we put n, so for general, so when we put n, so this gives us gamma n plus 1. Gamma n plus 1 is equal to factorial n. So gamma n plus 1 is equal to factorial n. So here n be the positive integer. N be the positive integer. Okay, so this is our general case. As per the previous parts, we have proved the value of gamma 2 is 1, gamma 3 is factorial 2, gamma 4 is factorial 3. So when we calculate gamma n plus 1, this gives us factorial n. Now, as per the above formula, so above formula is gamma n plus 1 equal to n gamma m. So now we have the formula gamma n plus 1 is equal to n gamma n. So on the basis of we can make this formula as gamma n plus 1 upon n. So we will use this formula also in several cases. So gamma n is equal to gamma n plus 1 upon n. Now we have some important properties also. So the important properties you can see that. So that means when we calculate the value of gamma n, so we have one property, gamma n is equal to infinity. Prove gamma n equal to infinity if n is 0. N is 0 or a negative integer. You remember this? Okay, when we have n is 0 or negative integer. So that means gamma n gives us infinity. So how to prove this? So we shall prove this by using the above properties. So that means gamma n, we have defined gamma n for only n greater than 0 means positive value, and we can take a gamma n plus 1. So we can take gamma n plus 1. This is defined for n plus 1 greater than 0. So when n plus 1 greater than 0, it means that n greater than equal to n greater than minus 1. So now we take a limit n tends to 0. So when we take limit n tends to 0, gamma n plus 1. So this gives us gamma n, when we put n equal to 0, gamma 1. So gamma 1 equal to 1. Okay. So now when we have the formula, that means formula is given as gamma n is equal to gamma n plus 1 upon n. So in this formula, we use this formula here. So we have already discussed in above. So here we put n tends to 0. N tends to 0 in above formula. So we see that limit n tends to 0, gamma n is equal to limit n tends to 0, gamma n plus 1 upon n. So n tends to 0 means gamma 0. Gamma 0 is equal to limit n tends to 0. Here we apply the value of n 0. So plus gamma plus 1, gamma 0 plus 1 upon n. So this can be written as limit n tends to 0. So the value of gamma 1 is 1. So this gives us limit n tends to 0, 1 upon n. So gamma 0 is equal to, now we apply the limit n tends to 0 for this. So we gives us 1 upon 0 and something upon 0 gives us infinity. So you can write down as gamma 0 gives us infinity. So the value of gamma 0 is infinity. Now we calculate for the negative integers. So here we see that gamma 0 is equal to infinity. Now we talk about the negative integers. So when we talk about the negative integers, so we take n is equal to minus 1, minus 2, minus 3, and so on. So we see that when we put n equal to minus 1 means gamma minus 1 is equal to n plus 1. N means minus 1 plus 1 upon minus 1. So this gives us gamma minus 1 is equal to minus 1 plus 1 0. So this is equal to gamma 0 upon minus 1. So value of gamma 0 is infinity. Infinity upon minus 1 gives us infinity. Okay. So similarly, when we put a minus 2, so the n minus 2 gives us minus 2 plus 1 upon minus 2. So this gives us -1 upon -2. So -1 is infinity upon -2 gives us also minus infinity. So every value, that means when we take the any negative integers, gives us the infinity. Okay. So the value of n is equal to 0, -1, -2, -3. These values are called singular points, are called singular points of gamma function. Singular points of, so remember this thing. So that are called singular point of the gamma function. So gamma function we have defined already by gamma n. So we write. Okay. So now we move further. That means other definition related to gamma function. So we have one property. You remember the property. Property says that the product of two single integral. Product of two single integrals can be written into the form of the double integral. Can be written in the form of double integral. So you can write down this. That means when we have a one integral a to b fx into dx, and another integral we have a c to d gy into dy. So this can be written as integral a to b c to d fx into gy dx dy. F, fx gy dx into dy. So we remember this formula. So we use this formula in few cases. Okay. Now we have very important part here. That means to prove that gamma 1 by 2 is equal to root pi. Gamma 1 by 2 equal to root pi. So we shall prove that here the gamma 1 by 2 is equal to root pi. So the proof is very important, or also we use in the questions the value of gamma 1 by 2 equal to root pi. So we know that by definition of gamma function, the definition of gamma function we write in gamma n is equal to integral 0 to infinity e raised to the power minus x, x raised to the power n minus 1 into dx. So this is our equation number 1. So here we put n is equal to 1 by 2. So when we put n is equal to 1 by 2, so we see that gamma 1 by 2 is equal to integral 0 to infinity e raised to the power minus x, x raised to the power 1 by 2 minus 1 into dx. So this gives us integral 0 to infinity e raised to the power minus x, x raised to the power minus 1 by 2 into dx. So this is our equation number 2. Now we use some substitutions. That means when we solve this integral, so it is quite difficult to solve. So we put x is equal to t square. So x equal to t square in this above integral. And what is the value of dx? The dx value is 2t into dt. 2t into dt. When we talk about the limits, so when we put lower limit, put x is equal to 0. So that means we put 0 equal to t square. So gives us t equal to 0. And for upper limit, so when we talk about the upper limit, put x is equal to infinity. So x equal to infinity. So this we can see that infinity is equal to t square. So gives us t equal to infinity. The limits are remains unchanged. So limits are same, t equal to 0 to t equal to infinity. Now we change this integral, that equation 2, into the form of t. So we write this as, so gamma 1 by 2, gamma 1 by 2 is equal to, the integral limits are remain same, e raised to the power minus x. So we put this as e raised to the power minus t square. E raised to the power minus t square into this value x. So we put x equal to t square. T square raised to the power minus 1 by 2 into dx. The value of dx is 2t dt. So we simplify this. So when we simplify this, so we see that integral 0 to infinity e raised to the power minus t square and t raised to the power minus 1 into 2t into dt. So t raised to the power minus 1 or into t, so this gives us minus 1 plus 1, t raised to the power 0, t raised to the power 0 is 1. So we take 2 outside from the integral, this is constant value, and we see that e raised to the power minus t square into dt. So this is our first value. So that means gamma 1 by 2 equal to e 0 to infinity raised to the power minus t square into dt. So this is the equation number 3. Now again we use the same property of definite integral. If a function, that means integral fx into dx, can be written as ft into dt. So we can write down ft into dt. So we again replace this t by x. So we write down this into the form of the x. So no issue for that. So gamma 1 by 2 equal to 2 into integral 0 to infinity e raised to the power minus x square into dx. This is our equation number 4. Now we put t is equal to y in equation 3. So we put t equal to y in equation 3. So we see that gamma 1 by 2 is equal to 2 into integral 0 to infinity e raised to the power minus y square into dy. This is our equation number 5. So from 4 or 5, so this is our equation number 4, this is our equation number 5. So we see that we do the product. Okay. So product, or we can say that multiplying 4 and 5. So we get, when we multiply 4 and 5, so we get gamma 1 by 2 to the whole square is equal to, so when we do the product, so this is 2 into 2. So we can write down 2 into integral 0 to infinity e raised to the power minus x square into dx into 2 into integral 0 to infinity e raised to the power minus y square into dy. So we have write the property above. So when we do the product of two integrals, so write into the double integral form. So you can write down this as 2 to the 4, 4 into integral 0 to infinity, integral 0 to infinity, e raised to the power minus x square into e raised to the power minus y square and dx into dy. So this equal to 4 into integral 0 to infinity, integral 0 to infinity, e raised to the power minus x square plus y square. Okay, base is same, we can add the powers. So we can write down the dx into dy. So here LHS is gamma 1 by 2 to the whole square. Now when we solve this double integral, so we solve this integral by using the polar forms. So use the polar form. So we convert this Cartesian form into the polar form. So when we convert Cartesian form into polar form by putting x is equal to r cos theta and by putting y equal to r sin theta. So square and adding. So we do the square and adding. So we write down the x square plus y square equal to r square cos square theta plus r square sin square theta. So this gives us r square cos square theta plus sin square theta. So this gives us 1. So this equal to r square. So that means x square plus y square we can put as r square. The value of x square plus y square equal to r square. So this is our first relation. So x square plus y square we can put directly r square. So when we obtain the value of dx dy, so the value of dx dy, so when we convert the integral dx dy, so this gives us r d theta dr. So double integral dx dy can be written as double r d theta into dr. So this thing we will discuss later in multiple integration. So we write down this as gamma 1 by 2 to the whole square is equal to 4 into integral. So when we put x equal to r cos theta, y equal to r sin theta, so the limits will also change. So x equal to 0 or here y equal to 0 to infinity. So when we put x equal to 0, so x equal to 0 gives us cos theta equal to 0. Cos theta equal to 0 means so gives us the limit as theta equal to 0 to pi by 2. Theta equal to 0 to pi by 2. And second limit we can write down as that means when we take the relation, so gives us r equal to 0 to r equal to infinity. So r equal to 0 to r equal to infinity, the limits of r gives us r equal to 0 to r equal to infinity, and limits of theta we have 0 to pi by 2. Because we have the relation theta equal to tan inverse y upon x in this form, okay, and r we see that x square plus y square. The limits of theta equal to 0 to pi by 2 or r equal to 0 to theta, 0 to infinity, and we put the value of x square plus y square gives us e raised to the power minus r square into dx dy, so gives us r d theta into dr. So this equal to 4 into, so first we solve for r, so we write down as theta equal to 0 to pi by 2. So this things we solve for r. So with this thing we solve for r. So that we put r square. R square equal to we can take as L, and 2r dr is equal to dl. 2r dr equal to dl. So when r equal to 0, L equal to 0, r equal to infinity, L equal to infinity, the limits remains same. So L equal to 0 to infinity, and this thing can be written as e raised to the power of minus L, and RDR equal to DL upon 2. So this is DL upon 2 into d theta. So first we solve this. So first we solve this. So we write down this as 4 into integral 0 to pi by 2 d theta. When we integrate this, so this gives us minus L or upon 2 or 0 to infinity. So 4 into integral 0 to pi by 2 into d theta. And when we apply the upper limit, so e raised to the power minus infinity, so 1 by 2 taken outside, minus minus plus, or e raised to the power 0, lower limit 0. So e raised to the power minus infinity is 0, e raised to the power 0 is 1. So 0 plus 1 gives us 1. So we can take a 1 by 2 as outside. So this gives us 0 to infinity, sorry, 0 to pi by 2. So 0 to pi by 2 into d theta. So when we integrate this, so this gives us 2 into theta and 0 to pi by 2. So when we apply the limits, upper limit pi by 2 minus lower limit 0, so this gives us 2 into pi by 2. So 2 to 2 cancel, gives us pi. So the LHS part is gamma 1 by 2 to the whole square. So LHS part is gamma 1 by 2 to the whole square is equal to pi. So then we can write down this as root pi. So the value of gamma 1 by 2 equal to root pi. So gamma 1 by 2 equal to root pi.